Good morning and welcome to the class. We were learning about the design of irrigation canals, and this is chapter number 4 from Irrigation and Hydraulic Structures by Dr. Iqbal. Last time we learned about rational methods, and there are several rational methods, and the one which we learned was Du Bois formula. And we also learned the permissible velocity method. Today, we shall learn the tractive force method. So first of all, let's see what's the definition of tractive force. The force exerted by the flowing water on the bed and sides of the channel is called the tractive force. And we can estimate the tractive force uh, by using this formula. This is tractive force for the bed, and we can get it by gamma RS, or we can replace R with the depth of the flow, gamma Y into S, and we will use this formula. So the method which is based on tractive force is called the tractive force method. Scour and erosion process can be viewed in rational way by considering forces acting on the particles lying on the channel bottom or the sides. The channel is eroded if the resultant force tending to move the particle is greater than the resultant force resisting the motion. This concept is referred to as tractive force. Okay, let's move forward. Let's talk about the distribution of tractive force. Now, the tractive force is different at the bed and on the sides. For the bed, the tractive force is gamma y into s, as we saw on the previous slides. But on the sides, because of the angle, the tractive force is less. The distribution is parabolic, but the average tractive force on the side is 75% of the tractive force at the bottom, 0.75 gamma y into s. Okay, the next thing is critical tractive force. Now, if the tractive force is too small, then the particles will not move with the flowing water. So for the particles to move with the flowing water, there must be a minimum tractive force, and that minimum tractive force is called the critical tractive force. It is the minimum tractive force, or we can also say shear stress, at which the erosion just begins. So our desire is that when the water is flowing, the tractive force which is generated should always be less than the critical tractive force, so that the particle would not move, means the erosion or scouring would not happen. So there comes the concept of permissible or allowable tractive force. It is the maximum tractive force that can be allowed in design without causing erosion. So as we all know, that we don't want erosion to happen. We want to preserve the cross section of the canal. So the permissible tractive force will be less than or at the most equal to the critical tractive force. Okay, let's move forward. Okay, the permissible tractive force for the cohesive and non-cohesive material is given in figure 4.10 and 4.11. I will show it on the next slide. And those values from figure 410 and 411 are for straight channel. But if your channel is not straight, then the tractive force can be reduced by the factors given here. Slightly sinus channel 10%, moderately sinus channel 25%, and highly sinus channel for 40%. So we can apply these correction factors. Then the next thing is tractive force ratio, or a reduction factor for the channel sides. So tractive force ratio is basically a ratio between the critical tractive force on the sides to the critical tractive force on the bed. So tau C of slope over tau C of the bed. And we can find out using this formula. In this formula, this theta is the slope of the sides of the channel cross section, and phi is the angle of the repose. I hope you know angle of repose from your geotechnical course. The effect of angle of repose should be considered only for coarse, non-cohesive material and can be neglected for the fine cohesive material. Okay, now let's see figure 4.10 and figure 4.11. 4.10 is recommended permissible unit tractive force for canal built in non-cohesive soil, and this one is for the cohesive soil. And you see on the x-axis you have average particle diameter in millimeter, and on the y-axis you have permissible unit tractive force in pounds per foot square. So basically we call it tractive force, but actually it is the stress. The units you see is pounds per foot square. And you see several figures here, 1, 2, 3, 4. For example, the first one is recommended values for canals with low content of fine sediment in the water. 2 is recommended value for the canals with high content of fine sediment in the water. So these curves belong to different conditions. Okay, moving forward, this graph will give you angle of repose. So based on the particle size in inches, which is on the x-axis, you can calculate from here the angle of repose in degrees. So you just have to select the appropriate curve. For example, this number 1 is for very angular, 2 is for moderately angular, and for example, number 6 is for very rounded. So it means that you should know what is the size and the shape of your particle. And for that purpose, you will have to do some geotechnical testing before you can begin the design. Okay, now here is the design procedure for the tractive force method. The steps are listed here, and I shall directly go to solving the problem following these steps. The only thing I wanna mention here is that we shall in this problem we shall assume a ratio of bed width to the depth of the water. So for different types of soil, you can appropriately choose these values. Okay, this will help you in reducing the number of trials. You will see in the end you will have to do trials. So let's solve our problem. This is an example 4.6 from the book by Dr. Iqbal Ali. Let me read the statement for you. Design an unlined earthen channel to carry a discharge of 60 cusic. I think the other problems we solved had also similar discharge of 60 cusic on a ground having an average slope of 1 over 1000. This method does not give us any formula to calculate the longitudinal slope. So we are using the slope, the average slope of the area where the canal is going to be built. The average particle size of the channel material is 0.25 millimeter of non-cohesive type. So the data is listed here. Discharge is 60 cusic, slope is 1 over 1000, and diameter of the particle is 0.25. This is, of course, the average particle size. So this can be classified as fine sand, for which the Manning's coefficient is 0.02. In the exam, I will provide you with the Manning's coefficient. Also, I will give you the angle of repose, which is here 34 degree, and it depends on the type of the material, which is in this case is fine sand. So this is the data which I will be providing you. Okay. So let's see the solution. First, we have to assume the side slope because it is fine sand. Sand is a non-cohesive material, so our sides will be very flat. So I'm using 3H2 1B, and using this we can calculate the angle using the tangent inverse. So it comes out to be 18 degree. Okay. Um, Assuming the we can assume the bed width to water depth ratio. Um, I'm starting with 5 just to show you that 5 will not give you appropriate result, and higher value, as I showed you on the slide where we have the design procedure, uh, around 7, between 7 and 8 would give you a better result, but just I'm selecting 5 to show that our result will not be very logical, and then we will choose the appropriate value later on. So the first thing I want to calculate is the tractive force ratio K. The formula was given, and this theta is the angle of the side slope right here, 18, and this is the angle of repose, 34 degrees. You solve it, you get 0.83. So by definition, this K is the ratio between the critical tractive force of the side slope to the critical tractive force of the bed. So that is 0.83. And if you rewrite this, therefore, the minimum shear required to dislodge the soil particle from the side slope is given as this. Means you move the TC bed to the other side, so you get the TC for the slope equals to 0.83 TC bed. Now, for stability, the shear stress actually generated on the side slope must be less than this value. This value is basically the critical for the side slope. As I said before, that permissible should be less than the critical, so that so that the erosion would not happen. And this is the critical, like this is our limit. Now, what is actually developed on the side should be less than this value, okay? Because this is the critical for the side. Actually, I should have used the side here. The slope and the side is actually the same thing. I will make that correction in my slides, which I will share with you. So we want toe at the side should be the actual toe at the side should be less than this 0.83 TC for the bed. Okay, we saw it previously on the very first slide, or maybe the second slide, that the shear stress developed on the side is 75% of the shear stress developed at the bed. Okay, so referring to the previous slide, it means that this T tau for the sides should be less than or equal to 0.83 tau C for the bed. This, if we ensure this, it will ensure the stability of the cross section. Now, this tau C for the bed is the critical value of the stress at the bed, and we want to keep the actual either less than or maximum equal to the equal to this tau C. Now, the figure 4.10 give us the permissible shear stress or permissible tractive force at the bed. So what we are doing here is we are equating, we are saying that the permissible or the allowable, we are saying it is equal to the critical, although we should keep it less, or the maximum value we can keep is equal to TC for the bed. So I'm replacing tau C for the bed with tau bed permissible. Okay, so if you look at this equation, we can simplify it for y and move everything on the other side, and using this formula, whatever y we get, we'll say, okay, the depth of the water should be either less than this or equal to this. If we do that, then the soil particles will not move, erosion will not take place. Now, in this expression, we know gamma is 62.4. We know the slope, it was given in the statement, 1 over 1000. This tau bed permissible, we can get it from figure 4.10. I cannot go back, but you can see in the slides, I have marked it there with a red line that for a particle size of 0.25 millimeter, the tau bed permissible is 0.085 pound per foot square. You can also use it as 0.080 It was very close, but in the book, the author used this value. So I'm just continuing with this value. So you plug this in place of flow bed right here, 0.0825. Gamma is 62.4 and S is 1 over 1000 or 0.001. You solve this, you get 1.51. So the depth you want to keep to avoid the erosion should be less than 1.51. So I'm just using 1.5. You can use 1.45, you can use 1.4, but just you should know that this is our limiting value. Okay, now this depth of the water. In the beginning, we assumed b over y equals to 5. If you do the math, you will get from here b as 7.5 feet. So you can say this is our first trial cross section. Okay, moving forward. So this is our trapezoidal section. B is the bed width. Y is the depth of the water. The side slope we assumed is 1:3. So it means that this distance is 3 times the depth. Now for this trapezoidal cross section, we have the formula for the area. We have the formula for the perimeter. Hydraulic radius is area over the perimeter. Velocity from the Manning's equation, it is in FPS unit, and then Q equals to AV. It's like a flow chart basically. And remember that this Z is basically this 3. So 1:3 is the side slopes, C3 is horizontal, and this C is equals to 3. So we want to do trials to achieve our desired flow, which was 60 cubic. We can make a table which is more appropriate. The first thing is y, which we calculated as 1.5 feet. B over y we assumed as 5, and b we got it from here. This ratio is 7.5 feet. Now use this formula and get the area 18 feet square. Use this formula, get perimeter 17. Use this formula, get R 1.06. Use this formula, get the velocity 2.5, 2.4, and then calculate the discharge using this formula, which is 44. So our required discharge is 60. So 44 is not enough. It means we have to increase the cross section. We will not change the depth. This depth is fixed to avoid the erosion. So we will change this V over Y ratio to 7. As I said in the beginning in the procedure, that for fine sand you can keep it like 7, 7.5. So use 7, get a new value of B, and get all the values. In the end you get 57, which is much better. Of course, our desired is 60. Change it a little bit, 7.5, do the math, and you get 60.7, which is close to our desired value of 60 cubic. It means that these dimensions are final. So our final design, depth is 1.5 feet, bed width is 11.25, side slope, it will give you a discharge of 60 cubic. The longitudinal slope is already given, 1 over 1000, which belongs to the area where the canal is going to be built. So that finalizes our design. So method is simple. The only thing in the end is that you have to do some trials. Okay. So this finishes the tractive force method, and I will try to assign you few practice problems for tractive force, and this also finishes all the methods which we had to cover, empirical and rational, for the design of unlined earthen channel. Remember that all the design methods which we have studied belong to unlined earthen channels. Okay. Moving forward, we will talk about few miscellaneous considerations that you should know as a designer. For example, the first one is about the longitudinal slope. Okay, let me read it for you. Longitudinal slope is fixed as per Lacey's equation. If slope of the canal is flatter, then the grade of the land falls are provided at suitable intervals. This is very brief information, just to give you the concept. Look at the uh, natural surface of the earth. You see, it is very slopy, but the slope of the canal, you see, this is a canal bed, is much flatter. So if you are in such a situation, then you provide what? Our drop. We call it fall, and then you continue on the same slope. And here you see the water level. So you clearly see there is a fall, and right here you see the actual picture of a fall. This fall is right here. We shall learn how to design fall later in the semester, maybe after the midterm. Then the side slopes. As you know, we always assume side slope sometime 1:1, sometime 1.5:1, sometime 3:1. For example, in the previous problem, we used 3:1. Okay. Uh, so side slope of the canal should be selected that remains stable under all operating conditions. Side slope range from 3H to 1V for lined canal, 2.5 to 3H to 1V for unlined canal, depending on the site condition. For example, if you have firm clay or for small channels, clay is very stable, so Z can be 0.5. It will still be, it's very steep, but because it's cohesive soil, it will be stable. But if as you move towards the sandy soil, the slope becomes flatter, and here it is 3H. Okay, 3H to 1B is much flatter. Okay, so this is briefly about the side slope. It means that you should know what kind of soil is there in the area before you decide the side slope. Okay, then the freeboard. We have been calculating freeboard. So what is freeboard? It is the distance between the full supply level of the canal to the top level of the cross section. It is just there for to accommodate any accidental flow or maybe rain. Sometime in the area there is rain and we get additional water, so there must be freeboard. Otherwise, the canal will overflow and may damage the banks, and that can, cause breaching. We don't want breaching, of course. So freeboard is the vertical distance between the full supply level and the top level of the canal bank. It depends on full supply depth and the discharge of the canal, and generally ranges from 1 foot to 4 foot for small distributaries and main canals carrying 3000 cubic discharge. For canal carrying 10,000 cusics or more, it can be 5.5 feet. This formula was, I told you before, this formula is provided by USBR, United States Bureau of Reclamation. F is the freeboard in feet, Y is the design depth, and C is a coefficient which varies from 1.5 for 20 cusic to 2.5 for 3000 cusic or more. In general, you can keep the freeboard as around 1 foot or a little bit more. Experience, will tell you, but 1 foot may be reasonable. Okay, moving forward, drainage behind the lining. Lining, this is about the lined canals. We will have one lecture about the canal lining. Right now what we have designed is all about unlined canal. So this is about briefly about the lining, and later on we'll talk about this in detail. Lining means if we make the sides and the beds of concrete or brick or some other material, then behind the lining we must provide some drainage, because even if we provide lining, there will be some seepage of the water. The water will cross the lining and go behind the side slope or below the bottom, and then that can create hydrostatic pressure. So we must provide some kind of drainage to drain that water in order to avoid the hydrostatic pressure. In case of hydrostatic pressure behind the lining, drainage of the soil behind the lining should be provided. Drainage may consist of filter blanket, or you may know this from the geotechnical course, or transverse and longitudinal drains under the lining. So whatever seepage water is here, the pipes capture that water and drain it somewhere, or maybe sometime put it back in the canal using the pumps. Okay. Then the next thing is super elevation. You may be aware of super elevation from the design of highways. you have studied a course about transportation engineering, and when there is a curve, so on the roads or the highways, we provide a super elevation, which means that the outer side um, is raised a little bit as compared to the inner side. Same thing, same practice is carried out in case of canals. So let me read it. Bed of the canal is elevated on outer side as compared with the inner side on the curves to overcome the effect of curvature, which is called superelevation. The effect of curvature is negligible if ratio of radius of curvature to the distance to the center of the canal is greater than 3 times bed width of the canal. Means for such situation you can just ignore it. You can calculate this H from this formula. H is the super elevation, V is the average subcritical velocity, B is the bed width, and G, of course, is gravitational acceleration, and R is the distance from the center of the curve to the center line of the canal. I mean, center line of the canal is somewhere here, and the center of the curve may be somewhere here. So that is basically the radius. Okay. Now moving forward, let's talk about the uh, cross section, uh, full cross section of the canal. Whatever we have designed so far is basically this trapezoid, only this trapezoid. But canal is not just this trapezoid. Canal has some other parts as well on the sides. For example, these are called banks, and this horizontal part between the cross section and the banks, this part is called a berm. Okay. Um, okay, here what is written is desirable section is partial cutting and partial filling. Just like the highways, when we build canals, we want that there should be the cut should balance the fill. Otherwise, we will have to either, for example, if the cut is more, then we will have to transport the material to dump it somewhere. Or the fill is more, then we'll have to bring the material from maybe far away to create banks. So that's why we always try to balance the cut and fill. Now this horizontal part, which is called berm, there are a few benefits. Let me read the definition. Berm is the distance between the edge of the canal section, right here, this edge, and the inner toe of the canal bank. Right here is the inner toe of the canal bank. So this part is berm. Berm width is usually kept 2 times the depth to 4 times the depth, where D is the, what is 2D to 4D? D is the full supply depth. So this right here, FSL, is called full supply depth. Okay. So this full supply depth, 2 times D to 4 times D. There are several benefits of this berm. I will mention few of them. For example, uh, they give additional strength to the banks and provide protection against the erosion and breaches. Means the water most of the time stays away from the banks, and that helps us in avoiding the breaches. The possibility of breaches get reduced because of saturation line comes more in the body of the embankment. Saturation line does not pass through the banks, okay, because the banks are far away from the canal cross section. They protect the banks from erosion due to wave action. Okay, sometimes there is wave action, although it's not very common, but sometimes because of high winds, there can be waves generated in the canal. Okay, and they also provide a scope for future widening. So if you have to widen the canal, you can remove the soil from the berms to increase the cross section. Okay, so you can read the rest by yourself. Um, Moving forward to the typical section of the canals, you see, what we have designed is basically only this trapezoid, right here, this trapezoid right here, and this trapezoid right here. As I said, that canal is much more than that. So the whole cross section is right here, is big. Now there are three scenarios. One is natural surface below the full supply level. You see here, this dotted line is a natural surface, okay? And it says natural surface above full supply. Full supply is right here, and natural surface is right here above. Okay, this is one scenario. The second scenario is natural surface level below the full supply but above the bed level. So this is the natural surface. It is below the full supply but above the bed level. Okay, and the third scenario is natural surface level below bed level. Right here, you see, this is full supply level. This is the bed level of the canal, and right here is the natural surface level. Okay, so you see, for example, here you see 2 times D. This is the berm here. Right here you see 3 times D. This is the berm here. Okay, and you create the banks, here on this side and on this side. There is road here. Sometimes we have road on the banks as well. Okay, we also have plantation. All this create stability and keep things far away from the water. Sometime in this situation, for example, you have this bank, and this is the full supply level. So right here is the hydraulic grade line. Sometime hydraulic grade line cuts the bank. If it cuts the bank, then there is a chance that erosion can begin and ultimately breaching can happen. So we protect the bank with help of additional mass of the soil, which is called pushta in our local language. So this is providing additional strength so that the hydraulic grade line would not cut it, okay, and would cut the ground. So the message is, do not think that canal is only this much. Yes, this is the most important part of the canal, which is the cross section where the water will be flowing. But when you construct the canal, the cross section is much bigger than that. Okay, so this was briefly about the typical cross section of the canal, and that concludes this part of the lecture and this chapter number 4 as well. I shall share these slides with you, and next time we shall begin a new topic. Thank you very much.